After doing laundry one night, I tried to hang my pants up and every hanger either bent in half or dropped my clothes. This was extremely frustrating and made me question how hard it could be to make a hanger that doesn't collapse on itself. This led me and my team to look into why coat hangers deform so easily and how the shape and material properties affect its deflection. To do this, we decided to conduct 3 experiments, the first using physical coat hangers, the second using FEA analysis, and the third using a MATLAB simulation. We conducted the experiment by applying a single point load on the hanger using a bucket and water as weight. We slowly poured water into the bucket until we saw a notable deformation. At this point, the team measured the height of the coat hanger and subtracted the original height of 7.75 inches to find the total deflection. We then used a scale to find the total force being applied on the coat hanger. We then repeated this process with different hangers at 2 different forces to help verify our experimental data at multiple weight samples.
When doing the CAD for the FEA, accuracy is of the utmost importance. So, to do this, we imported a picture of the coat hanger, scaled it to the proper dimension, and then traced it with the line tool. Using this, we swept it with the diameter congruent with what we measured via caliper, and then we also added the superfluous geometry such as the twist around the neck of the hanger, just to ensure that our FEA was as accurate as possible. A fixed constraint was added around the hook of the hanger. This simulated what it would be like for a hanger to hang on a rack. A single point load was added to the center for ease of mathematical calculation. Then I plugged in both sets of force values, 2.8 pounds and 4.2 pounds, and ran multiple meshes to ensure that the values converged to a common value. The result of this was that the most of the deformation happened around the straight portion of the hanger, with some deformation around the bent corners of it.
The final step in our analysis of the frame deflection came in MATLAB, where we used mathematical theories to model our structure's deflection analytically. We treated the frame as a triangular structure to simplify calculations. First, we initialized variables, ensuring that all material properties match the hanger and the FEA's properties. Then, we used MATLAB functions to calculate the bending moments at thousands of individual points along the beam. From here, we used the moment curvature equation to calculate the beam's deflection under the point load forces used in the experiment and the FEA analysis. This equation works due to the simplification that the beam is pinned at its ends for this section. The deflections were then normalized to ensure that the ends of the beam had 0 deflection due to its pinned end simplification. Next, we sought to find the deflection caused by the 2 supporting sides of the hanger. To do this, the new width of the hanger was calculated by knowing the original width of the hanger and the deflection of its center. Then, with the new width, the new height of the hanger was calculated using trigonometry, and this allowed us to find the deflection of the ends of the hanger, adding to the overall deflection of the bottom beam. This display shows the resulting values after calculating the hanger's deflection in MATLAB under a 2.8 pound force, compared to the experimental data as well as the FEA results. As shown here, when compared to the average deflection of the hanger on both trials, which is about 3.36 inches, the FEA analysis is within 4% and the MATLAB analysis is within 6% of accuracy. This display shows the resulting values after calculating the hanger's deflection in MATLAB under a 4.2 pound force compared to the experimental data as well as the FEA analysis. As shown here, when compared to the average deflection of the hanger across both trials, which is about 4.595 inches, the FEA analysis is within 3% and the MATLAB analysis is within 10% in accuracy. With all of this in mind, our predisposition about metal hangers deforming too easily was clearly proven, as quite small loads were causing massive deflections and degradations of the hanger structure. However, when we looked at other similarly shaped objects that handle similar loading patterns but at higher weights, like a cable pull handle for working out or a waveboard handle, we wondered what caused them to be so much stronger than a coat hanger. The obvious answer to this was the material used, and while that certainly plays a part, it doesn't tell the whole story. We reran our FEA analysis of the hanger, but instead of the natural shape of the hanger, we kept the wire gauge the same and made the hanger into a solid triangular frame. Doing this showed that the maximum deflections were between 77 and 80% less for the triangular frame. This proves that even metal coat hangers we use every day could be more resistant to deformation, but due to the cheap manufacturing processes for our current designs, I doubt we will see any manufacturers switch to the strictly triangular frames in the near future.